We're going to revisit a concept of molecules and atoms in that 602 times 10 to the 23rd number, but we're also going to revisit dimensional analysis and we're going to take it a step further. So, as we've seen before, you should have already known how to describe and maybe even calculate moles and molar mass. By the end of this video, you'll also be able to convert the moles to number of particles of a gas using dimensional analysis and use chemical reaction equations to convert between measurements of different substances. The question the video will answer by the end is typical airbags in small cars require approximately 65.1 liters of nitrogen gas to inflate to the proper size. In order to do that, what they place is a sodium nitride compound as a solid because of the metal that's in it inside your steering wheel, and that when it gets hit by the compression will turn into sodium solid and nitrogen gas. To generate the nitrogen gas, we want to know how many grams of the sodium nitrate must be included to generate that big bubble that you see. And there's a little hint that the density of nitrogen gas at the temperature at which it inflates is 0.916 grams per liter. So we're going to come back to that. We're going to be able to figure out how to go from 65.1 liters of nitrogen to grams of sodium nitride. So first, let's talk about the mole roadmap. Last time, we talked about how to convert between moles that you see on the left, that little mole guy, and gram per molar mass, or mass of the substance using gram per molar mass. Now we're going to talk about how to convert it to particles. So using the 6 times 10 to the 23rd number, a mole is always that amount of any substance. Notice that mass and particles are not connected. There's no straight conversion between mass and particles because each particle has a different mass. So you're going through the mole unit in order to get from one to another. So keeping that in mind, let's do an example. It's the easiest way to talk about it. And we're going to use dimensional analysis. So we're going to calculate the number of molecules in 4 moles of lithium sulfide. Some people know what they're going to do is just multiply 4 by 6 times 10 to the 23rd because every mole has 6.02 times 10 to the 23rd particles. So if you have 4 of them, you'll have 4 times that number. But if we're showing it in dimensional analysis, we would put the 4.00 moles over 1, that's the number in the question. We would multiply by a new fraction to have the same unit on the denominator of that fraction, so 1 mole. And we would say the denominator of 1 mole is equal to 6.02 times 10 to the 23rd. This setup shows that we're going to multiply the numerators and get 2.41 times 10 to the 24th. I also already checked my significant figures. The 4.00 has 3 important numbers. So does the 602 because times 10 to the 23rd is just a placeholder. It's just a lot more zeros. So 602 are the only ones that are measured. So we kept 3 sig figs at 2.41 times 10 to the 24th molecules. The 10 tenths to the 24th are not measured, but they're really important because it shows you it's a really large number. Let's do another example. It says calculate the number of atoms in that question. So notice that lithium sulfide, Li2S, is a molecule because there are more than 1 pieces. There are 2 lithiums and a sulfur. So for every 1 molecule of Li2S, you would have drawn 3 little circles to represent what Li2S looks like, right? It would be 2 lithiums and a sulfur. So for every 2.41 times 10 to the 24th molecules, there are 3 times that number of atoms. So if I took that 2.41 times 10 to the 24th molecules and placed 1 molecule on the bottom of the next fraction, that would be equivalent to 3 atoms. So we're multiplying by 3 to get 7.22 times 10 to the 24th. Again, do you have to use dimensional analysis to solve this? Some people knew to just multiply by 3. Fine, but we're using this to solve harder problems in the very near future. So let's do another easier one. How many moles are present in 1.2 times 10 to the 24th molecules? So we're going to place that number over 1 in a fraction. And when our new fraction, which we're multiplying by, the molecule word will be on the denominator of that fraction. The molecule word always gets the 602 times 10 to the 23rd particles number. I don't always write the word molecules. I probably should have for this. But I always think that the number's pretty big, so it reminds me that it is the molecule number. And that's equal to a mole of any substance. So again, that numerator and denominator are equivalent to each other, and which is why they can be written there. Since these are catty-cornered, we're dividing 1.2 times 10 to the 24th divided by, that's what the line means, 602 times 10 to the 23rd. And that gives us a 2. Remember, I'm not going to just write 2. I'm going to write 2.00 because both of these numbers given in the question and the 602 number have 3 important numbers. And so 2.00 has 3 important numbers, or sig figs. Some people, again, might have noticed that was exactly double the mole number, and they would have known it's 2, but we're showing dimensional analysis for practice. Again, just think, why do chemists use moles to measure substances? Why aren't grams or liters or molecules enough? So again, considering that mole roadmap, we mass things in grams and we find volumes in liters, and those are really easy things to do in a lab. But just because you scooped up some mass or some volume of a substance does not mean you know how many particles there are in there. And the only way to figure out how many particles there are in there is to go through the mole calculation, right? To go from grams and liters to moles and then to molecules. That way we can know exactly how they'll react. They react molecule for molecule, not gram for gram. One molecule will collide with another molecule, right? So if we want to know how they're going to react, we talk in molecules. But if we're doing it in a lab, we talk in grams. And moles is our conversion. So let's do another example. Calculate the number of atoms of phosphorus that are in 120 grams of P2O5. So we're going to place the 120 grams given in the question over 1, and we're going to multiply by a new fraction. If grams is on the top of the first, it will go on the bottom of the second, and that grams comes from the reference table. So 2 phosphoruses at about 30 grams each, as well as 5 oxygens at about 16 grams each, gives us a total of 141.94 grams. That's equal to a mole, which is why they can be a conversion factor. Now that moles is on the top, is moles the thing that we wanted? Unfortunately, moles is not what we wanted, even though 1 mole is equivalent to 141.94 grams. We're not quite there yet, so we're going to set up, as you can see, a new fraction where we multiply one more time. Since now moles is in the numerator of the new fraction, it's going to be denominator of the next fraction. So that way, grams is always catty-quartered, moles is always catty-quartered. 1 mole is also known as 6 times 10 to the 23rd particles. So 1 mole can be equivalent to a grams, and 1 mole can be equivalent to a particles, but grams and particles are not equivalent. Right? You have to go through the mole number. What this means is we're going to divide by denominators and multiply by numerators. So I, in my calculator, do 120 divided by 141.94 times 602 times 10 to the 23rd. And sorry, I forgot, we're going one more step. We don't want to know how many molecules there were. We want to know how many atoms there are. P2O5 is a molecule, so that's why I said a mole is equal to that many molecules. But 1 molecule P2O5 is actually equivalent to 2 atoms of phosphorus. Notice they only ask for phosphorus, and there are 2 of them in that chemical. So one more conversion factor where the molecules are catty-cornered, and 1 molecule is equal to 2 atoms. So we're going to do all this calculation, 120 divided by 141 times 602 times 2. And our final answer is 5.073 times 10 to the 23. If you're thinking about sig figs, 120.0 had 4 important numbers. Anything with a decimal counts those zeros. This has 5. This has 3. And whenever you do counted numbers, like there are 2 atoms and it's exactly 2, you don't worry about numbers that are whole like that. So that means the least number we should have is actually 3, and I should have rounded this to 5.07 times 10 to the 23rd. Many AP questions will give you information about a reactant using an equation and ask you about a product form or vice versa. So you're going to need a balanced equation to create a mole ratio and convert between the moles of a substance. So we're going to talk about balancing in a few videos. For now, I'm going to give you the balanced equation, and you're going to have to convert between the substances. So the best way to learn is through examples. The example we have is water decomposes into its elements when electrified at high voltages. If 24 grams of water is completely decomposed when it gets electrocuted, how many grams of oxygen will be produced? So just as we learned before with dimensional analysis, and this is why we learned dimensional analysis for these harder questions, we're going to start with 24 grams of water on the top of the first fraction over 1. We're just following those rules, and the rules say that if grams is on the top of that fraction, it will also be in the bottom of the next, and the grams come from the grams of water from the table. So if you add up 2 hydrogens and an oxygen, we get 18.016 grams, and then we say, what is that equivalent to? Well, the only place you could go from grams on that mole roadmap was moles, and that's equal to 1 mole of the water particularly. I don't want to know about moles of water. I, again, want to know how many grams of oxygen I want. So I need to find a way to get from water to oxygen. And the only way to do that is use this ratio in the equation that they gave me, that for every 2 molecules of water, I will create 1 molecule of oxygen. So I'm going to use that as conversion, that the water will go in the denominator so that way they're catty-cornered, but 2 of them are equivalent to 1 oxygen. Sorry about that announcement. So anyway, again, catty-cornering the water and moving it into oxygen, we're almost there. So since now we have oxygen, we have the moles of oxygen. I want to get to the grams of oxygen. So one more time, if moles is on the top of that fraction, we're going to put moles on the bottom of the next fraction. And 1 mole of oxygen is equivalent to, if you look in your reference table, 1 oxygen would have been 16, but we have O2. So it's 32 grams for every mole. Again, just looking it over before we calculate it, grams, grams counting quartered, moles, moles counting quartered of the same substance, water, water. Moles of oxygen, moles of oxygen. And the numerator and denominators are equivalent to each other. 18 grams is equal to 1 mole of water. 2 moles of water are equal to 1 mole of oxygen. 1 mole of oxygen is equal to 32 grams. And the only way to convert between one chemical and another is through a mole ratio in this reaction. Mole ratio. You can't convert it between grams, unfortunately. Now in your calculator, what we would do is 24 divided by 18016 divided by 2, because it's a denominator, times 32. And our answer is 21.3 grams. So what we've said is if you use 24 grams of water, you'll get 21.3 grams of oxygen. Any clue as how much hydrogen you would have? Well, you can go through this math again and change it to hydrogen, which would be 2 moles of hydrogen, and hydrogen's mass on the top. But another way of thinking of it is conservation of mass, right? If I start with 24 grams, I have to end my equation with 24 grams as well. So if I start with 24 grams of water and I ended with 21.3 grams of oxygen, the rest of it has to be hydrogen, which is like another 2.7 grams. So rather than doing all that work, you can say, since there's only one other chemical present, it has to equate to the rest of 24 grams. Let's try this one more time with another equation. Lithium and magnesium chloride react in the equation below. Calculate how many atoms of magnesium we would make if 2.5 grams of lithium are used. So we're going to start with 2.5 grams of lithium over 1. We're going to multiply by a new fraction where grams of lithium will be in the bottom from the reference table, and that's equivalent to a mole of lithium. Notice I always label the lithium so that I know that lithium will go into the denominator of the next fraction. The words should cancel. For every 2 moles of lithium from the equation, I will get 2 moles of magnesium. So that's kind of nice. And last, anytime you're talking about a mole of substance, which will be catty-quartered, so it will cancel, it will be equivalent to 6 times 10 to the 23rd molecules if it was a molecule. But since magnesium is one thing, it's an atom. Now in your calculator, you're going to do 2.5 divided by 6.954. You could decide if you want to times 2 and divide by 2, but that's kind of cancels out. And multiply by our big number, and we'll get 21. Oh, I was saying it's supposed to be 2.13, sorry, times 10 to the 24th atoms. So to go back to a question in the video, what we're going to do is start with the 65.1 liters of nitrogen. Since we have no conversion factor from liters to molecules right now, we're going to use the density formula. So if the density is 0.916 and the volume is 65.1, when we cross multiply, we'll get a mass of 58.6. We're going to take those grams and we're going to divide by the mass of nitrogen, so that way we have moles of nitrogen. We're going to change nitrogen into NaNO3 using the equation that there are 3 in front of the N2s, and there's a 2 in front of the NaN3s. And last, we're going to change that to grams of NaN3. So 6502 is from the periodic table. And when we divide by 28 times 2, divide by 3 times 65, our final answer is 90.7 grams. So they have to grab out 90.7 grams, tuck it away inside that bag, and tuck that bag away inside your car steering wheel. And then if you get into a collision, it triggers fire that decomposes the NaN3 into that big bubble of nitrogen gas. At this point, you should be able to convert between particles of a gas in the moles as well as different measurements of different substances using chemical reactions.